Good morning, everybody. Thanks for coming. You already know that I'm Christophe, and what we are going to do today is we are going to make a snake game. Yeah? And I know that some of you have very few experience with Haskell, so we are really going to take small steps. I made a lot of effort in trying to make analogies so that the material can be digested really fast, I hope. So the challenge for the 2 days is to make both snake, and it's going to look approximately like this, and then Tetris. Everybody knows what snake is, yeah. Right? Yeah. Because when I was telling this to my PhD students, they were telling me like, you should watch out because some of these kids will be too young to know what snake is. So that's not a problem. Okay, so who am I? I'm a professor in computer science at the U Ghent. I teach the following courses: functional programming, logic programming, and also foundations of programming languages. So this goes about type systems and so on. I love Belgium chocolate, football, and running. And I guess that's enough. So also, if you like to, there is also going to be a short presentation moment at the end of a monadic party, where if you have made something that you think like, I didn't know anything about Haskell, and look at this super cool game that I made in 1 week, then you can show this. And I would recommend everybody to show their game, right? So that's an option if you would like to do that. So without further ado, we are going to begin with just like the basic concepts. So we are going to look at list functions, algebraic data types, and the library called Gloss in order to make the graphics of all these things. Okay. So this is more or less the what we are going to do today, but we're just going to dive in. So most of you who have already installed Haskell and so on will have noticed that it has a read eval print loop. Yeah? And that just means that you can use Haskell as a chat box, sort of speak. And so we can just talk to Haskell. And so let's start our first conversation with Haskell. Actually, at this point, I see a lot of people on their laptops. At this point, you don't need to do anything yet on your laptop. I'm not saying that you cannot do anything, but it's not necessary for following the talk. So the first thing, if we are friendly people and we are having a chat box, the thing that we could do is like just say hi. And so when what Haskell responds is, well, the variable hi is not in scope. Yeah? And so it says, perhaps you meant pi. So let's try that. And then we get pi. Okay. So Haskell seems to be knowing a lot about math. So we can also try something else, right? We can to put hi like in another programming language, and we put it between quotes, and so it responds with hi. Yay, we got something. So then we do 1 plus 1, and because we think Haskell knows a lot about math, we get 2. Yeah? And then we try to hack the system, of course, and we write 1 plus hi like we did last time, and we get something strange. Basically, yeah. For a beginner, this is like, what the hell is going on, right? So it says no instance for num, and then between these braces, arising from a use of plus. And I remember using Haskell for the first time, and you get like this kind of error messages. And the first time, if you have not seen any Haskell, this of course doesn't make any sense. So what we are going to do is we are going to look at this type error, yeah, because it's something with types. Yeah. Luckily, people use types all the time. Yeah. For example, here is a typing example which is being used every day. Everybody knows how to do this. This is like the type car, and this is like not cars, right? It's most very simple. But we don't just use cars. Yeah? I mean, we don't just use types. We make categories of things. We also categorize these types themselves. Yeah? So, for example, everybody can identify this as a convertible car, right? And so we actually have what is called a class of convertible cars. Yeah? And so what's the difference between a normal car and a convertible car? Well, it's defined by the operations which the car supports. And in this case, we could say a convertible car is something that can convert itself, right? Everybody is following? This should be quite easy. But then what we do a lot in Haskell is like we raise the abstraction level a bit higher. Because we have been looking at a particular instance, we have been looking at a convertible car, yeah? And so we can make a class of convertible things, yeah? And then we can make an instance specifically for the car. And then you have a convertible car, a convertible desk, or a convertible sofa, but they are all characterized by the operation that they support. So this is a type class operation, and it's still convert. Yeah? So we have started from like, well, you have cars, yeah? That's a type. And then you can make a class of cars, and then we have abstracted even farther, and we have made a class of convertible things. Yeah? And the biggest thing is that this type class, it's all of these instances, they need to have an operation convert. That's what characterizes them. That's why we say that they are an instance of convertible. Yeah. Okay. So this was this was the analogy. Let's now take this into Haskell. So we have integers, for example, and then we have not integers. Yeah. So the Boolean types, floats, and strings, which are lists of characters in Haskell. And so we can make a class of num. Yeah? And a class of num, it's something that supports add, subtract, multiply, and a number of other operations. Yeah? So, and then, so num, something numeric. Yeah? And then if we make, there are lots of instances of something numeric, for example, integer, double, and float. They all support add, subtract, and multiply, and so on. Yeah? Everybody is with me? Okay. So we were talking to Haskell, and so, we tried to say hi. That didn't work. That kind of worked out, and then we got into this type error. But we can further talk to Haskell. And so the thing that we are going to ask is like, could you give me some more information about this num thing? Yeah? And then the answer, more or less, is going to be, well, num is a type class with the following operations, and I found these instances of the type class. And so if you do that, let me just show you for real. Is this big enough? Okay, so the way you do that is you type double colon I, and that's telling Haskell, I need some information. And then you type the thing that you want some more information about. So in our case, we want to get some information about num. And so we just press enter. And what we see is that it says, well, this is Haskell's way of saying it's a type class, class num a, where, and then these are all the operations that are supported. And I'm going to go a bit more in detail about this definition shortly. But what you also see is that there are a number of instances, for example, word, integer, int, and float, and double. They all implement these operations. Yeah? It's exactly the same as with a car. Yeah? With a car, there was one operation, convert. Here there are multiple operations, plus, multiply, and so on. Okay. So let's look a bit more in detail to the definition of this type class. Right? So this is a type class, and so first you write class, and then you give it a name, and you say, well, this is a type class, and the name is num, and this is what is called a type variable. And so this type variable is going to be filled in at the moment that you make an instantiation of your type class. And so in this case, we have one operation, plus, and it takes an A, yeah, the type. So this is reading as the type of the plus operation. Well, it's something that takes two A's, yeah, an A, and then two A's, and it returns you an A. So let's fill it in for the integer, and then you have to replace all the A's by integer. Yeah, so in this case, the plus operation, well, it takes two integers and it returns you an integer. Yeah. Okay. This type definition, you can read it in two ways, right? You can read it as, this is something that when you give it an integer, it's going to give you a new function that is still waiting for another integer, and if you apply that new function, it's going to give you back an integer. Is that making sense for everybody? I see a lot of people nodding. So. Okay. So let's go back from where we started. We had this 1 plus high. Yeah? And so what Haskell at this point is saying, no instance. Yeah, so it's like this thing of this type class. And then we see num here, right? And so let's see. I'm going to give a Rubik's Cube to to ask people questions. So the basic idea is that I'm giving a Rubik's Cube, and then if you have the Rubik's Cube and I ask a question, you're supposed to answer. Yeah? I know that this sounds scary for some people, and if you don't want to answer, you just pass on the Rubik's Cube to somebody else, and that's it. But it's a very, at least for me, it's a very good indicator to know whether you are following or not. And in general, asking, is everybody following, usually doesn't work. So I'm going to start here, and you just pass it on. So now that we have gone through all the trouble of looking at what the type class is and what these instances is, so do you now understand what's going on here?
I think so. So the compiler says we don't have a type class instance for an array of characters.
Yeah, exactly. And that's because we have been using it here with this plus. Yeah?
Right. So.
And so first of all, it's probably looked into the num for int and so on, and it saw that that it doesn't match, right? Because why didn't it match? Well, there is something called type inference in Haskell, and so whenever you write this 1 plus thing, it's going to try to infer the type of 1. It's going to try to infer the type of high. It's going to find that this is going to be something hopefully numeric, and this is going to be like this string of this array of characters, right? And then it's going to try to match all these type classes. Yeah, but let's look at this type class again. There is something very important here to see. Yeah, the left side and the right side of the plus operator, it needs to be the same type. Yeah, and so it probably checked first. Well, can I do something with this 1? It failed. Then it went on to the right side. Can I do something with the array of characters? And then it saw like, well, there is no instance for num car. So that's that's why it's not working. Okay. Yeah.
I wanted to ask, is it actually possible to make this work in language by implementing a type class?
Yes, you could make a a type class, not a num type class, because for the num type class, the left and the right side of the operator, it needs to be the same type. Yeah, but you could make a num prime AB, which takes an A and a B and returns a B, right? And so like this, you could define some operator about plus, but then I think you also need to hide this plus because the operations themselves need to be distinct. Okay. So in 20 minutes we went through types and type classes and these instances, and we could kind of understand now what this error means, right? But there is still a big question: where do these types come from, right? It's not we haven't defined these types ourselves yet. Okay, so this is just to make things light. Well, basically there is an algebra for that, and that's from Arabic, and so it's the study of mathematical symbols, and then the most important for what we are going to see, it's like the literal meaning is the reunion of broken parts. So it's going to take elementary pieces and it's going to construct bigger things about it. And so the way that you make new types in Haskell is with something called an algebraic data type. And so it's an algebra with mathematical symbols for making data types. And so I didn't know who invented this, and so I went on a Google search, and so it turns out that the Hope programming language, which was still before Miranda, and so it's from 1980 that some clever guys invented these algebraic data types. And so if you want to read up on the original paper, that's the paper where they first described this. And so the big difference, because there were some things like algebraic data types already at that point, is that they closed it off. In the early versions, you could have like all these algebraic data types could be open and you could extend them at any point, and that made things a little bit more difficult for the type inferencer and so on. Okay, so we are going to start with a very easy algebraic data type, and just to show a little bit the use of this. So for example, is the snake touching the apple? Is the snake eating itself? And so on. We want to have a Boolean data type for it. And so basically, we need to somehow tell Haskell, well, there is something called true and false, and they are mutually exclusive. So either it's true or either it's false. Okay. So how do we, of course, Haskell already has Boolean types, so we can just ask Haskell, like, give me some information about bool. And so the same as we did before, we just type :I, we ask something about bool, and then we basically get the definition. So the definition itself is, first you write data, then you give your new type. This is really a type, bool. You give it a name. Yeah? And then what you see is this on the right-hand side, you define how you can construct Boolean types. Yeah? So you say, well, let's define a new type. The name is bool, and it has two constructors. The first one is called false, and the second one is called true. And by convention, these types and these constructors need to have capital letters. Okay. That's the first thing. Now, there is something really strange in Haskell. We can define exactly this. We can say, well, we are going to define a new type, which I explicitly didn't give any meaningful name, foo. and we say that there is one constructor for this, and it's also foo. Yeah? And I remember that this kind of pattern is being used a lot in Haskell programs, and it's very confusing because this purple foo is something completely different from this red foo. Yeah? So this foo, it's a type. Yeah? And this one, it's a constructor for making something of type foo. Okay. So, does everybody understand this part? So, okay. Let's look at a more advanced data type. Let's look at lists. And so, of course, we are going to use lists in our snake game. And basically, a list, it has like the head and the tail. And so, if we look at this, these are Haskell functions that you can use over list. And so the head gives you the first element of the list. Init gives you everything except for the last one. Tail gives you everything except for the head of the list. And last gives you the last element in this list. Okay, so the way that you write it in Haskell is with these braces and then a comma between the elements. And so just as we did with bools, we can also ask, give me some information about lists. Okay. And so this is a bit of a weird thing because this is actually the name. Yeah, but with these curly braces, you can also write. You can write it explicitly like this, but you can also put the A between the braces. So the way that you read it, if it's standing like this, it's like a list of A. Yeah, it's either the empty list. Yeah, and again, let's see whether you got this. What is the difference between this list and this list?
So left one is a type and right one is the constructor.
Yeah, so this is the constructor for the empty type. And so this A, and then we have the cons operator, which concatenates an element to the front of the list. Yeah, so we have a list is either an empty list or an A, and then concatenated with something here. What is this something here?
It's like another list.
Yeah, so is this a type or is this the constructor at this point?
I think it's a type, yeah.
Yeah, it's a type. Very good. So it's honestly, I think this is a bit confusing. This is the constructor, and here we say another list of A's. So let's read this again. We define a list of A's to be either the empty list or an A and with the rest of a list of A's, where this list of A's again is a type. Okay. So lists, they are super important. There is a whole programming language, one of the earliest programming languages in the world. It's called Lisp, and so the name derives from list processor. And so in Lisp, everything is about lists. So if you have not encountered Lisp or Scheme or Racket or any of these languages, it's very much recommended to take a look. Okay, so let's come back to the algebra of algebraic data types. So the way that you write it down is you say data, then you say, well, this is the name of my new type. You then have a number of type arguments, and then you have a number of constructors for that. Okay. So let's do this interactively. So let's see. I'm going to make it even a little bit bigger. Let's see whether we understand now what these types are exactly. So if we ask Haskell double colon T, so not I, then we are going to ask the type of the expression that you write here. And so T of true, what is it going to give us? Yes. Okay. And so let's let's do something very strange. Let's ask what is the type of bool? You cannot know this, but we are getting something like this. The data constructor is not in scope bool. Yeah? And why not? Because bool itself is a type. Yeah? And so asking the type of a type makes a lot of sense. Yeah? But there is another way of doing this. And so this is what is called kinding. So if we write double colon K bool, yeah, we are going to get the type of a type, basically. Yeah? And so if we ask double colon K of bool, we get star. Yeah? And so this is, and they even use the same symbol here. So, but you have to read it differently. So the kind of bool, it's star, right? So, and star, it's the type of all proper types. Okay? So what would be the kind of int, for example? Also star. Yeah. You can pass on the Rubik's Cube. And so now there is a really difficult one. So what would be the kind of list?
Is it the type or the constructor? The type, right?
Because we wrote double colon K, it's going to be the type, yes.
I know the answer because of I'd guess star again.
Star again.
Well, it's, you use data, right? Instead of type parameter. Yeah.
It says star to star. Why is that? Well, a list on its own, it's not a complete type. Yeah? Because basically what Haskell is going to tell you, yeah, a list of what? Yeah? So it's just list. It doesn't have kind star, just like int and bool, because it's basically waiting for a type to be filled in to be a proper type. And so this is also why there is this arrow here. So if you give it a proper type, it's going to give you back a proper type. And so that's the kind. Everybody is following? Okay, so let's do this. What is this going to be?
It's star at this point because it's given the type int and then it turns into the type.
Yeah, exactly. And so what I was saying before, you can use exactly, you can use also this notation. So that's the same. And this notation is used a lot more. Yeah? But I use this notation to give more the feeling that this is some, it's like a type level function, right? So a list, it's waiting for another type to make a type. Yeah? Okay. I think that we have been going through this. Okay.
Round phrases, do they have a meaning?
The what?
The round phrases.
They do have a meaning because they change the precedence of the operations. But in this case, I think I could have left them out. Okay, so how is everybody doing? Like, is everybody following with the kinding? Yeah. If not, please tell me now. well, you paid for this, so it's your time. So it's your time, and if you are not following, you have to tell me, and everybody else needs to wait and listen until everybody is with us, because all of you are here because you like this, right? So we are now going to look at functions, and so these functions, they are very different than in other programming languages, in the sense that they are mathematical functions. And so a mathematical function, it basically is going to give you the same result for the same input. Yeah? It's impossible for a mathematical function to have an arrow from this triangle to this red dot, and also from this from the same input to something else. Yeah? So they can map to the same y value, yeah? But they cannot have two arrows going out from the same input value. Yeah? That's the really big thing that you need to remember. They are it's really a mathematical function. So let's look at a very simple example. We can add two numbers, and so what you do is you give your function a name. Yeah, there are some arguments, in this case x and y, and then you write equals and then the expression, which is like your function body. And in this case, the only thing that we do is we add x and y together, and that's the result. So what is this top thing? Well, that's your type annotation, and it's completely optional. You don't have to type it in, but usually it's good practice to write the type annotation for all your top level functions. And so in this case, how do you read this? Well, I define a new function add, and it has this type, namely it's a function from integers to another function that takes an integer to an integer. And so let's play around with this, because I want to show currying. So now we have defined the add function, and we can also ask now what is the type of add, and we see that in this case it's a bit different, right? On the slide it was integer and so on, but what Haskell did is it has seen that this function, it just uses plus. Yeah? And so it basically derived, well, in order to add things together, this thing, yeah, this x and y, they need to be from the num type class. So the way that you read this function signature is, well, assume that we have an a from the num type class, yeah? Then it's going to have this type a to a to a. Yeah? And then of course you can use this with integers or float and so on. And so if we now write add 4, this is a nice feature of Haskell which I wanted to to show. So we are now defining a new variable, which is a funny name because we cannot change variables in Haskell. So it's more like a constant. So let add 4 equals add, and we only supply it with one argument. Yeah? If you are coming from another programming language, this sounds really weird, because we have defined add, it takes 2 arguments, and you're calling it with 1 argument. Yeah? So what's going to happen is that this add 4, it's going to like partially apply this function, and it's going to give us a new function back, which is still waiting for the y argument here. Yeah, everybody's following? So if I have add 4, and I press enter, and now I call this. Let's first look at the type. So it's exactly what I've been saying. So it's still waiting for an a, and it's going to return us an a. Yeah? And so if now I call add 4 with 1, what are we going to get? 5, of course. Yay. So that concept that you can apply functions with fewer arguments, and then you get a new function which is still waiting for the rest of the arguments, that's called currying. Yeah. Yeah.
In the REPL, is there any difference between let and skipping let? We define add with let, without let, and add for with let.
Yeah, so the thing is, in the newest REPL, you don't have to put a let anymore. But in older versions of GHC, you had to put the let explicitly, which is nicer, because if you don't write a let, there is an implicit let, yeah, and so it's a bit weird because everybody has been telling you that you cannot change variables. But if you write add 4 equals add 3, it will simply say like, okay, that's fine. And now if we add 4 with 1, we get 4, which is weird. But what happens is that if you type this into the REPL, you have an implicit let, and that implicit let is actually making a new binding. Yeah? And so you're actually not changing the original binding, you're just nesting the scope. Is everybody following what I'm saying?
It's
so
shadowing.
Yeah, it's shadowing. Add 4 equals something, and then let add 4 equals something, and so here. So what happens is there is an implicit let, and so the first binding, it's something, and then the second binding is something else, right? And so when you look up this add 4, it's going to first find the latest definition, yeah? But the other one hasn't been changed, yeah? So it's still, it's not like you can change the variable, but it looks like it.
Can you unbind the list?
Can you unbind? Probably, but I don't think so, no. Okay.
Is it valid to bind, let's say if you wrote a normal Haskell code, would it be valid to let and then let that for be something and then something else?
Well, there are different kind of lets in in Haskell, and so this is like one kind of let, and there are different kinds because you also. But I'm not going to go into that at this point. But there are different kind of lets, and so yes, you can use let in your normal Haskell code, but you have to watch out a bit because depending on where you use let, it's going to mean something different. Okay, so when we make function definitions, we can also use pattern matching, and pattern matching is something super cool. So we define the Fibonacci, and it's a function which takes an integer and it returns an integer. And so instead of writing here a variable, so for example x or y, we can actually use a value here. Yeah? And so what's going to happen is that Haskell, when you call the Fibonacci function, it's going to look at the argument, and if it's 0, it's going to go into this branch, and it's going to return 0. If it's 1, it's going to return 1. And in all the other cases, because this one is always going to match with whichever number that you give it, it's going to call recursively the Fibonacci of n-1 plus the Fibonacci of n-2. So I assume that everybody has once implemented the Fibonacci. So, but the most important point is here that you can use pattern matching on numbers. Okay. You can also use pattern matching on data types that you define yourself. So, for example, if you have made a new definition, so you have made a new type day, and you have Monday, Tuesday, and so on, and then you can define, for example, a function next weekday, and you get this. So you can just use pattern matching to see which constructor that you passed, and that's That's how you can define it. Okay, so let's look at Quicksort. So Quicksort, everybody kind of, so the idea is that we are going to sort a list. And so in this particular case, we are going to sort a list of ints, and we are going to give back a list of ints. And so here we use pattern matching, and we say, well, Quicksort of an empty list, that's super easy. It's just the empty list, right? The Quicksort of a list, yeah, and here is where we also use pattern matching. So remember this double column, it's like the concatenation, yeah? Everybody remembers? So this means that whenever we pass a list, we are going to deconstruct it. We are going to deconstruct it in the head of the list and the rest of the list. Yeah? There is a lot on this slide. And so then we are going to make two new lists. Yeah? We are going to make a list of all the elements which are smaller than this head element. Yeah? And then we are also going to make a list which is bigger than this head element. So how do we do that? Well, we use what is called a list comprehension. And so in mathematics, you probably all remember. So this is basically making a new list of x's for which holds that x has been picked out of the rest of this list, and then with the condition that x is smaller than h. Is everybody following with this? Okay. And then for bigger, what we do, well, we make a new list of x's, and we are going to pick these x's out of the rest of the list, and we are going to, but with a condition that this x is bigger than h. Yeah? Okay.
Wouldn't it also possibly get out elements if you do strictly bigger or smaller?
Like a less than or equal to h? Because if you have a bunch of threes.
Yeah.
Well, wait. So, you're saying that if there are multiple values with the same, then so wait, if this equals the h, then it's not going to be in there. Yeah, it could be. It could be that they are filtered out. One of them should be equal. Yeah. Okay. Let's do. Yeah. Okay, so let's practice on this list comprehension. So if we want to filter out all the elements bigger than, let's say 5, bigger or equal than 5, how would we write that? Who has a cube? Yeah.
X pipe.
Yeah.
I can't remember the syntax name. X less than 5.
So first you need to say, well, we are going to take x's and we are going to select them from a certain list. So in this case, it's literally list. And then we are going to put a condition on that x with a column. So we say, well, we are going to make a list of x's where we are going to pick x out of this list with the condition that x is bigger or equal than 5, like this. And then we get 5, 8, 9. Okay? So how, if this is what is called a tuple. And so we can also pick 2 elements. Yeah? So in this case, we could make like all the combinations of picking two items from this list and putting them in a tuple. And so, for example, if we just write then y, you just also take this from the list when we get all the tuples. And so Python also has like these list comprehensions, but if this is the first time, this is super cool. You can write super cool programs with this in a very very short time. Yeah. Well, I'm going to take a break here, and then after the break we are going to see more list functions, and then we are also going to start implementing Snake. So it's 10 minutes. So let's say that we start again at 11.
Earlier in one of the slides, I wanted to double check that, I think I probably just saw it wrong. We did type of num, like :t num, versus kind of num. Where, like num is a type of.
So let's just see. That doesn't work.
Yeah, right.
Right?
Yeah,
So what we,
that's what I expected.
so what we did is we asked some information about num.
Right, yeah.
So that's double colon I.
Yeah, which makes sense. I just wanted to double check earlier in the slides that we'd done :I of num and not :t of num. Okay, cool. I was misremembering, I think. Yep.
Well, it could be, but I don't think so.
No, makes total sense.
So we started with the I. So we did I of num. So all the slides are going to once I've done with the slides, I will put them on Discord, and so you can look at it. But I don't like to give out the slides because then people usually just look at the slides and know all the answers and they are not thinking anymore. Well.
Is there a possibility of something else will be working from a files?
It's coming. It's coming. So
Because it takes a lot of time to download anything.
It's 600 kilobytes. It's fine.
Okay, yeah, I know. Just like stack install can take it. That's all I'm saying.
You don't have GHC installed?
I have it, yeah. It's
Yeah.
just not local to the project. So when you run stack install,
No, I don't use stack.
okay.
But yeah, and the thing is that you're going to get a login to an online platform where you can practice the exercise. So if you run into some problems with your installation, you can still work. It's not ideal, but you can still work. What is the type of num?
Sorry. Word implements num.
Mhm.
But how can I create a word? Like, I guess.
How can?
How can I create a word? Like, I
How can?
guess.
Ah,
if
but
I type like a single quoted, like.
Or does it like you can machine size it?
Oh, that type of word. Okay, never mind. I take it back.
Look. So it's a very good. There are actually two things that I should still show. But if you want to know this, you can just type in, "Hey Haskell, give me some more information about Word," in this case. And so it's a bit cryptic because it's basically going to tell you that it's built into Haskell. Basically, that's how you can look at it. So.
Is the data constructor for a word just a W then? Like if you did W7 or something like that, it would give you a word? Is that what it's saying?
Well, it's basically like this prim, and in this prim there is like the constructor of a that's a type of a word, I think it depends on the architecture that you're running it, but I'm not 100% sure. So it's either 32 or 64 bits.
They're also explicit word 8, word.
Yes, you can use all these.
But in order to create a word, you can do word space 7, right? You do 7 colon colon, I think.
I'm not 100% sure.